And okay, cool. So for K-nearest neighbors, now we know how to measure how far something is from each other, right? Using our distance metric and stuff like that. And like I said, we'll probably use Euclidean distance because it typically performs well. Though I was reading something like, for example, saying like, oh, would cosine similarity work well on K-nearest neighbors? And basically like, no, like it doesn't usually perform very well. Although some data sets like the iris data set, which we'll show in a second, actually does perform pretty decently with the cosine similarity, but it's more of an exception than it is like a typical thing. So kind of just know a little bit. All right, so K-nearest neighbors. So like I mentioned before, just when we're talking about distance, right before we talk about distance metrics, it's a classification algorithm. It is a supervised learning. So we need to know essentially what the classes are to train it. And then once we have that, we can actually determine, like basically we can predict what future points are based on how close they are to other points. Okay. And what's nice when I say close to, it doesn't have to be 2 or 3 dimensions. It can be as many features as you want. Now, I'll say as many as you want, they'll obviously perform differently if you have like 1,000 features versus like 3 features. But the basic idea here, and this is actually from the curriculum, just this part, is essentially what we say is like, okay, we have these blue points and we have these yellow squares over here, and we have this red circle right here. And what we're trying to figure out is like, hey, what is this red circle? Like, is it supposed to be a, what's it called? A yellow diamond? I guess it's still a square. I'm gonna say diamond or square, yellow square, or a blue circle, right? And the idea here is that we'll use, well, who's near you? Like who is the most near you? So in this case, you can kind of see if we consider only the points that are in this dark circle right here, okay? That means like, oh, you can kind of see already, it's like, oh, this is how far they are. You can see that, for example, the yellow is most close to it. There is a blue one, but it's kind of far away. You're like, okay, well, you're probably close then to these squares. But you'll notice that there's also this dotted line here. So imagine instead we only consider the ones that are in this dotted line, okay? And you can see here, it's like, even though there's two yellow squares just right next to it, there's also 3 blues that are in here. So there's more blues than there are yellows within the square. So maybe in this case, like, oh, maybe if we consider in this case, maybe this one's actually closer. So we can actually do the average distance and figure out how far basically are they from all these different points. And that's where this K part comes in. You only consider the K nearest neighbors, the 3 most nearest neighbors, or the 5 most nearest neighbors, hence the K. So it actually turns out a big part is going to be actually finding the K. But that's the overall kind of like idea here. And here I actually have this little graphic from DataCamp that kind of talks about K nearest neighbors. But this is essentially the algorithm. Essentially, you have a new data point. So you have all these classifications. This is like essentially what's nice about K nearest neighbors. You don't have to train it. Like basically having the data is trained. So what you do here is you take this little point and you say, okay, how far are you from all of these, you know, the first like 10 or 5 or whatever points? Basically, well, actually you would have to do it for all of them, right? But basically because you don't know how close they are, you say, okay, how far are you from all these different points? And then you say, okay, only consider the first like 3 points, so K equals 3. And say, okay, we look at this part and you say, all right, based on this, right, on those who are closest, how many are actually in here? So in this case, there are 2 green and one red, this one red star. That would mean that this would be classified as green, or the green triangle, okay? So the idea here is that we actually use the distances to figure out who is near it, and then we say, whatever's the most in there, that's what you are. So in this case, if you only had K equals 3, the 3 most nearest neighbors, it would be a yellow square. And then if we had 5, we would say, okay, there's 5 of them in here, 5 of the most, 3 blues and 2 yellows. These 3 blues would say, oh, well, you have 3 of them already, so this is also going to be blue. And that's how we basically balance between saying how far you are and who's nearby you. Okay, makes sense? Cool. All right. So some advantages. So I mentioned there's some advantages, maybe some disadvantages. So advantages is that it's lazy learning. Basically, there's no training. The training is literally just having the data. So if you have all the data already labeled like this, right? Basically, you just say, all right, calculate all the distances. So remember, when we get a new point, we don't know where it sits. We have to calculate all the distances. And once we calculate all the distances, we say, all right, only pick the first top 3 or top 5 or top 10 or whatever, right? And say, okay, based on those top neighbors, how many are you? And that makes it really easy to interpret. Basically, the idea is like, well, the reason why it's labeled this way is because there were more of that type or that class near this point, okay? So it's not like it's deterministic. There's no, randomness to it. It's kind of like very straightforward in the sense of like, once you know the distances, it's just like, oh, we just pick what's the majority that's close by. Okay, makes sense. Cool. So some disadvantages. So I'm gonna ask you guys, what do you think might be the disadvantages using this kind of algorithm? There's gotta be some disadvantages, right? Because this is lazy learning, like that's sweet. Like there's no training phase, and we'll see other machine learning algorithms that take a long time to train. This is like instant. So what do you think we trade off by having no time to train? And this actually will be a really common theme with all computer science, is if we can do something very, very quickly, we usually have to trade it off with something else. And this is where like go a little physics on here, it's not really, but like space-time. So essentially we have to have more space. So that's always going to be a conflict between all like our algorithms for any computer science thing. Is like how much space does it take and how much time will it take? And those will trade off where it's like, oh, we can save a lot of time, but it's going to cost us more space. Or we can save a lot of space, we can do a very small thing, but it's going to take more time. Okay. This is always going to be like fighting concepts back and forth. So that's what the big disadvantage is. Basically, you have to keep it in memory. So when we say space, I'm talking about like how much do you have to store? You have to store all of these features or all of these training points with all of their features. So in that case, it's not going to have, there's no training phase. However, it means that you have to store this thing. So if you have, 2 gigabytes of information and you want to put this on a phone app, for example, for someone to use, 2 gigabytes is a pretty large app for just someone to like do some classification. So you can also imagine this, people talk about IoT stuff. It's like if you wanted something for a stakeholder that are using IoT stuff and then want it on the edge, like they call it on the edge, basically training on there. Well, KNearest Neighbors is not going to fit very well on there. If it's up in the cloud or something like that, you're like, cool, like we'll just load the data up there. There's basically use the data that's already stored. We could save like 500 gigabytes, right? And it's perfectly fine. And then send the predictions back down. But not all cases make sense for that kind of thing. Okay. Some other things that beyond just basically its space is that it's not robust. It doesn't generalize very well. And so the way that you can kind of think about this is that when you have all these points right here, right? And you say, okay, if I have a point right in this, I don't know, you guys can see my cursor, right? Yeah. So you can see like where my cursor is like, oh, if there's a point right here, clearly red star, right? Point over here, clearly green triangle. The point right here, it's not super clear exactly what this should be. Like we might end up being a green triangle, but it might not really make sense by itself. So that's why I mean it doesn't generalize very well. It's like if it doesn't have an example on this like certain area, it doesn't do very well. And this is actually going to be really important for something called cluster dimensionality. So it turns out when you have higher dimensions, many, many features, you are more likely to have things that are sparse. And by sparse meaning that they're not going to be in spots that there are already a lot of points, which I think is not super obvious by itself. Like one example of this of cluster dimensionality for mathematics is they talk about putting like I'm going to do this very briefly, so I'll go too far into mathematics. But you basically start off with saying, okay, let's start off with a square and make a inscribed circle. And then from this point, basically say, okay, what's the biggest circles we can make that will inscribe that big circle in the square? And you're like, okay, like those are pretty far, like those are a certain distance apart. But if we did this in 3 dimensions now, and it's going to be kind of tough for me to draw, but like imagine like we had like a cube. And then we put in that cube the largest possible ball in here that's going to touch all edges. So I'm not going to really draw that, but you can imagine this ball. And then say, okay, in these corners, like how big of a, like smaller balls can we put in that would touch this ball in the box? Okay, and basically, oh, how far, like how much volume would this have? And it turns out as you go in higher and higher dimensions, like 4 dimensions, 5 dimensions, 6 dimensions, which remember are just like features. It turns out these balls end up having larger radiuses than this original square. And people are like, wait, what? Like, and it's kind of interesting. People describe it like as spiky balls and like higher dimensional, or like, what is this going on? And basically just means there's more room for available in higher dimensions. So this cluster dimensionality says like, well, we're going to have more room. And since we have more room, it means that we need a lot more points to fill in those same spots. So the problem is if you have like 10 features, that means you're going to have not as many options to put them in. And I think this kind of makes sense when you like square things. Like if you imagine like how much room do we have on a single line, and then we square it. Like, well, now you have a lot more room like all inside this. And if you, go up one the power, you have even more space. It basically keeps increasing. So that's where this cursive dimensionality happens. So you probably won't have an example in higher dimensions and more features that will actually make sense over here. Okay, does that make sense? Okay, cool. I didn't have to do too much math, so that's good. All right. So you guys basically know like 4 or 5 dimensions now, like pretty easy. But anyway, one way we can kind of do this, kind of fix this is something called PCA. So we're learning this, I think next week. And then also higher dimensions, we can use cosine similarity. So remember how I said like, oh, like cosine similarity, not useful necessarily for K-nearest neighbors. That's partly because it's not very generalizable. But if you can, cosine similarity makes a lot of sense for higher dimensions because now you don't have to worry about how many dimensions you actually have. Also, I mentioned here, soft boundaries are troublesome. So what I mean by here is that like, if you imagine, right here, it's really clear. It's like, oh, there's a clear boundary right between these two. But if you had a bunch of like, kind of mixing parts, I think kind of like this, where you can see like a little bit of the blue, like maybe there's like a yellow here, blue here, blue here. It's not super clear where that boundary should be drawn. It's kind of fuzzy. It doesn't do as well because basically it doesn't know, well, things that are close to it, it's like, well, it could be either or. So you're gonna get this weird mess and the boundary's not gonna be that great. Okay, so those are those disadvantages. And this is why like, it's nice beginning supervised learning because it's like, it's super easy. Like, it's like, basically you have the data, you're like, oh, look, I'm done training, awesome. And then the next part basically is easy to interpret. It's like, oh, well, if it's close to it, like if there are more that are close to it, that's what you are. Okay, cool. No questions? Not pretty good? Okay. So one part in here is that's going to be the hardest, or not the hardest part, but it's the main meat of the K-nearest neighbors is actually determining which one is K. So like, do we consider like, K equals 1, like the very first point, K equals 3, all these points? And I think if you guys look at the curriculum, this is actually that image from here. So like, okay, you're trying to figure out, how many neighbors should we consider? And basically the answer is you kind of don't know. Like you kind of have to essentially see what the data, what does well in predicting on this data. And this is where we have our training data. Our training is just our labels, right? And basically we're trying to find this K, which is what we call a hyperparameter. Essentially it's the thing that determines really how we classify, not really the training part, if that makes sense. But that K basically is like, okay, we have to try out the models. Like, what if we do it with 1? What if we do it with 2, 3, 4, 5, up to 10, or whatever many you want to try? And from that point, we say, okay, that's how it performs. And this is where basically, like I like to mention, we really should talk about like our training set, our validation or dev tests or dev set, and our test set. So essentially you have your training, it's all labeled. Your validation is basically say, okay, how do you use that to determine K, basically what performs the best. And then after that is your test set. It's like, okay, now that we figured out what K is, let's see how well it performs on data that it has never ever seen. And that's essentially how you would kind of like evaluate how well it performs. So one way we can determine K is using an elbow plot to test out our error. So I think this is also from the curriculum itself. Basically you increase the number or increase K going through, and usually it's between 1 and 20. Like obviously you need at least 1 for K-nearest neighbors, but usually about 20 is about as high as you really need to do. I'm trying to think of situations. I mean, I could maybe see something where it's higher, but usually after 19 points, it's pretty good. It's not going to really perform any better. And what you'll see, this is called an elbow plot, and you'll see this kind of thing where basically we're increasing this K, we're seeing how the error is, and eventually what will happen, the error will kind of drop down. And what will tend to happen is that it'll kind of level off. This might not be the most realistic by itself. What you might see is something that looks kind of like this, where you start off with high errors and then it drops down probably pretty significantly and then kind of levels off in this way. Sometimes depending on the situations, this is where like, for imagine if you count like 50 of your nearest neighbors, well, that might be like the whole data set and stuff like this, your error is going to start going up again. So that's why like about 20 is probably realistic, and you probably won't keep going low, 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 low here. It'll probably level off at some point and probably start going up. And what you want to do then, if it'll look kind of like, you'll see this very commonly. There we go. You'll see kind of something that goes like this. You want this lowest point. And if it starts leveling off, you want the simplest K, right? So like if it starts leveling off to like exactly this part, like it doesn't make sense for you to consider a bunch of other points, you might as well just stop at the earliest k when it stops decreasing the error. Okay. Makes sense? And that's how you would determine k. And usually it's between 1 and 20. Okay. Quick question. What would happen if let's say I have 50 data points and I go all the way, let's say I have actually 20 data points. So I have 20 data points in my training set, right? That's a really small, but let's just pretend. And I go up to k equals 20. What would it predict it to be?
Whichever class is more numerous.
Yeah, right. It'll just guess it. Let's say red is more common. It's just going to guess red every single time, regardless of where it is in the set. So that's why you have to essentially limit how many points you have. Okay.
Is there some room? So when I'm making an elbow plot, and let's say it does kind of hit a minimum and stay kind of flattish, is there room for me to kind of make a judgment about how much decrease in error is not enough to bother? You know, do I get to say, oh, the error decreased by 1/10,000th. I'm just going to go with the previous one.
Yeah.
Can I do that? Okay.
Yeah, and this is actually a concept called early stopping. So in here, it's k, but there'll be other hyperparameters that you can tune for other machine learning models. And essentially, it's like you don't want to keep tuning it until like it's the absolute minimum and then comes going up, because then that means you're kind of in a sense overfitting. Like it's still only performing well in valid. This is why like I know the curriculum mentions about train versus tests. There really should be a train versus validation, because what happens is that as you try more and more different hyperparameters on your machine learning model, you actually end up overfitting onto the validation set over the training set. And that's because you're trying a whole bunch of different things. So your actual validation might actually, like your model tend to overfit. This is actually a good kind of concept that is good to mention, because I think we mentioned about Kaggle before. Are you guys familiar with like Kaggle competitions? Okay, so do you guys know how they kind of work with the competition, like how that structure kind of goes through? Okay, so just really brief. Okay, so really briefly, what it does basically is that you have a data set from Kaggle and say, all right, here's the data set everyone would have. It's like labeled, or let's assume it's a supervised learning problem. So you have it all labeled and say, okay, here's the data set. You train on this. You can decide, sometimes they give you a validation set, but sometimes you say, okay, here's all the data. You decide what the validation is, and you go ahead and try to figure this out, okay? So you train your models, you give it through, and then once you're done with your model, you can submit it to Kaggle. And what's kind of cool is that you can submit this multiple times until the deadline. And what happens is that when you submit it, there's a public leaderboard, and it says, how well you performed. And so, for example, the first few ones people try to submit, and the public leaderboard usually hovers in like a pretty bad scores, like you weren't very good. And then over time, as it gets closer and closer, people get better and better scores, like, oh, let me make this tweak, make this tweak, make this tweak. And you'll see people climb on this public leaderboard, but they've never seen this actual data. All they do is say, here's my model, tell me what the error is. And they can see the error is like, oh, you have like a 0.5 accuracy, you know, oh, you have a 0.6 accuracy, 0.8, 0.9, like 0.999. Like, oh, sweet, like you're very close on that public leaderboard. However, when the competition finally ends, they don't judge on the public leaderboard. They go to another data set they haven't shown anyone. That's the private leaderboard. And that will be the one that determines everyone else. And what's really interesting, if you ever look at this on Kaggle data set, like competitions, you'll usually find people who are very high up, they'll actually drop down some. And that's because they start overfitting on the public leaderboard. Even though they've never seen that data, they're just tweaking the model until basically it performs really well on here. And that's what you want to avoid basically with your training, your validation, and then that's why your final test. Your test is kind of like that private leaderboard. Does that make sense?
Okay. So in a competition, you would want to use your judgment and kind of like, you know, I'm gonna not go for that 99%. I'm gonna stop at 90 and hope that keeps me from overfitting. Like, is that how people play it?
Not even that. It's because you do want to perform well on the validation set, right? The thing is that if you can perform well, let's say if you actually know what's going on, like you have the perfect model, you know exactly, like theoretically how everything works, which means you'll perform well on the private. You will score well on the validation, or you likely will score well on the validation. You know, there's a chance it might score a little lower, but still, you will still score pretty well. So the problem is, it's determining, are you overfitting on that public, or are you actually doing the right thing and getting a better score? And that's where essentially it doesn't matter necessarily just the feedback. You have to decide, does it make sense that my model, like for this data set, does it make sense that I'm overfitting, or is this realistic, or is this unrealistic, or what kind of approaches am I doing? And that's the really tough part, is understanding when, without ever actually looking at the direct numbers by themselves. And yeah, that's why overfitting is always an interesting kind of problem because it's more like the technique versus like just the feedback you're getting back. Okay. Yeah, question though. All right, I thought that was an important part because that's what our next part's a little going to here. And we'll talk a lot about overfitting, underfitting. So you can imagine here, here's a little harder example. Like, to be honest, this is going to be closer as an example for like decision trees and support vector machines than like K-nearest neighbors, but you can do something similar to K-nearest neighbors. Essentially, you can imagine like what's going on here with them trying to find what this point is, like within like, you know, this random set, is essentially trying to figure out where this line comes to there, where you determine where these points are, like where the boundary is of like these different points of how they're labeled. So you can imagine if you have a really bad model, so it's called underfitting, right? It's too simple to explain this variance. Basically it says, oh, just take this cross through here. Well, it's obviously making a little too simplistic. It's being too simple with this single line, okay? Versus something that's like what you actually want is this guy right here, where essentially, okay, it's a little complex, but you can see here is that we're catching the point. Note that the right fitting still makes a couple mistakes, but for the most part, you might be fine with that because maybe these points really are like outliers. Like maybe they shouldn't be really considered as like, you know, mistakes in that same sense, right? But it's not super clear like exactly how you define this. So you have to be kind of careful, right? But the point is like, it's okay to make a few mistakes. And then overfitting, which in a lot of ways is almost like, if you ever get like a model that performs like 99% or 100%, immediately you suspect, oh, it's no good, because what happens, you can technically make these boundaries all around here, but you can see it's a little too complex. It's too good. Essentially, it's being a lot of, it's being too confident. And that's like, oh, I know how to go around this part. And this might be true. However, this might have just been a mistake. And so if there is another point that's blue here, like let's say right here in the real like test set, this will still, as it say, oh, that's actually an X. Where in reality, it's like, well, no, that really should have been a blue, you know, here. It's just that you were overfitting. And this is what we want to avoid. This usually is pretty simple to do. Oh, I'm not performing very well. My values are really bad. This is like, this is seductive, if this makes sense. Like this is easy. It's like, oh, look how well my model's performing. Where in reality, you're just overfitting and actually becoming a bad model. You want this nice Goldilocks zone. Okay. So nice overfitting. And then let me talk about the Kaggle thing. So this would be kind of like, this would be the validation set, this red and stuff like this. It could also be training. And then like there's an actual testing set that basically would show that this model is overfitting or underfitting, which you can see already it's underfitting. Okay. Cool. So going back to sklearn a little bit, how much should I do? Okay, I just plotted this part. So I'm just going to show you guys this part, is that I have an iris data set. So I think I've used iris before. Have I shown you guys that? Cool. I'll use it a lot because it's a nice little, it's not too big. It's a nice 150, right? It's well known. So note there's 3 different classes. I'm only using 3 features. I think there's more than 3 features. I remember there's like, I think it's 4. Actually, it might be 6. I can't remember. I think it's 4 though. But anyway, I'm only using 3 because we can see in 3D. Past that, good luck. So anyway, so you can see here the different points, like class, you know, I think this is class 1, class 2, and class 3. So you can see how they're kind of grouped together. Okay, and there's a distance in here. So we can use K-nearest neighbors. So what's cool is that we're going to go ahead and use sklearn's neighbors instead of implementing it by scratch, because let's be honest, we probably won't be doing that too often because there's not a reason to if it's already made. Plus, it's less likely to make mistakes because it's being looked over for many, many people. And note that I'm just putting the metric as Euclidean. Note that if I didn't change the metric, it still would have been Euclidean. That's the default, it turns out. But we're going to go ahead and create this classification. We're going to say, let's try 6 neighbors. So note that normally you would try this with many, many different neighbors, but you can see like, you know, I'm just defining 6 neighbors. Let's say I already determined it in some case. And I'm going to go fit it on this XY. So this fitting, even though it's at the training stage, is really all it's doing is say, hey, load the data into the K-nearest neighbors. Okay, so you can see here, it's all fit, all set and ready to go. And now we can say, okay, let's go ahead. I just put these random points. I think this actually came from, I think this might actually be the example, but these are just some random points on here. Oh no, I think I did create these points. Anyway, you'll see what these points look like and what the predictions are. So you can see here that for each of these points in 3 dimensions, we labeled as 2, 2, 2, 0, 0, 1, 1, 0. So, okay, that's what its prediction. We'll have to see, does it make sense? So we'll go ahead and see also its probability. So saying how likely is it actually making these, how certain is it for each of these points? So you can see here, for each of these points in here, you can see basically it's pretty certain that it's class, you know, 2 in this case. Pretty certain it's class 0. This one, it's pretty certain, but it's not 100% sure. Like it's 83%. It's possible it's class 1. And you see this very last point here, this 333, which if we look on this point, let's hear 3. Where's 3 over here? 3 and 3. It's like right here. So you can kind of see it's probably determined between these 2 points. It's like in the middle between the red and the orange. Okay, the top and the bottom. So that's why it kind of says 50-50 chance. Okay. So what's nice now is like, okay, let's just go plot it. So note that I don't have any actual classes because I think I made these up. I'm pretty sure I made these up. Okay. So I'm just putting those in there and say, okay, like how do they compare when you actually plot them out? And so I made them slightly bigger. So S equals 400, just basically making points. So all these very large circles are those points and what they were labeled as. So you can see here, it's like, oh, that's a pretty decent job, right? Kind of going through. But note that, you know, for example, this red point, I think this is the 3-3 one. Yeah, this 3-3. Note that it makes sense that this was like really like 50-50. It wasn't really sure because there's not really examples over here. So I was probably considering these points over here. I wonder if I actually put in like, let's just try this out real quick. I put in like 4 points. Okay, and still the same training data and stuff like that. Oops. And you can see here, that's about the same too. I was wondering if I could try to make it guess wrong, or at least poorly. So let's try to do 2. Oh, that's too good. All right, so 2 looks like to be pretty enough. It's about the same. But you can see, like, you know, if I had changed in different K metric, let's try something extreme like 20. Wow, it's just too close together. I picked 2 good points that were actually pretty clear. But you can kind of see, like, you know, you can imagine, like, if you somehow were able to include this one, like if I move this point maybe down like to here, it might be like fluctuate between yellow and or like orange and red, back and forth, because it's not really sure. You can also imagine, like, if there's just more points that are orange and I put in something like, you know, like 100 or something like that, it might just consider all these oranges. Yeah, you guys want to try to see that, I guess? Go for it. Okay, let's try something extreme, 200, because I know there's not 200 points in there. Oh, I see, it's too good. Let's try 100. Okay. Now we're getting some differences. Yeah, so you can see here is that there's more gray in this case because I'm considering too many points. So it's considering like this point saying, oh, 100 nearest neighbors. Well, you can see there's this weird crossover right here. So it's going to start counting this part. I think it's 175 total. So I wonder if I can get, I'm trying to get it as close as possible to the actual value. No, it's still going. It's too good. Let's try 150. There we go. All red. So you can see here is that basically, I think I reached to the point where it's basically the most are red. So it's just guessing all of them are red. So you can see that basically not more Ks is necessarily better. So you can imagine if I were to plot this error out to see like how well it performs. Good. Cool. All right. So that's implementation. And you can see it's actually implementing it. Like this is literally me implementing it right here. Like that's the whole thing. Right? Most of this stuff is just basically for you, me to load in the data, plot it out. Even this prediction, this is already made here. You can see most of the work is basically being done right here. Okay. And I have put a little label here just to show you where KNearest Neighbors. You can see our algorithm. Here we go. Metric. So the metric is Pinkowski, and then you would set the parameter for whatever this certain metric is. In this case, the default is 2. So it'll be literally the Euclidean distance. Okay. Oh, also kind of a fun fact, I skipped over this. Manhattan distance is the same thing as L1 regularization. So if you imagine like L1 regularization, that was absolute value. Euclidean distance, L2. Okay, so you can kind of see that kind of commonality in here. Cool. I think, yeah. Now I was wondering if I got those points from somewhere, but I don't think I think I made them up just to kind of see what things were like close by. All right. Cool. Any questions you guys have for KNearest Neighbors or?
So some examples of problems that I would try to solve with KNearest Neighbors would be things like assigning a genre to books or movies. Like that's a KNearest Neighbors issue, right?
Yeah. So like things that you want to try to find similar groups, like classes of things, right?
Yeah.
Yeah. So you can think of like genres. Like that one would be tough. I'm trying to think exactly like what the features would be. Like in that case, but it could be something like even just guessing someone's like age, like are they a teenager? Are they a what's it called, like an adult, are they a child, based on maybe their listening habits of like, let's say a list of things and stuff like that. So they're different features. So the idea here is like there's some grouping, and note that there's a subtle concept here is that we're assuming things that are very similar to each other, like that should be in the same class, are actually physically close together, which it turns out that tends to be true. Basically, things that are in certain groups like class 1, class 2, class 3 tend to have similar features. Note that depending on your data, that might not actually be true. Like you can imagine maybe like, I don't know, let's just pretend like you're trying to predict, based on someone's listening habits, if they're in California, Oregon, or Colorado. And it turns out people in California and Oregon basically have interchangeable features. Like there's not really a distinction between the two. This wouldn't perform very well, but basically no algorithm would perform very well on that because there's no distinguishing features. So that's why K-Nearest Neighbors can work. In reality, you probably won't see K-Nearest Neighbors too often in production just because the disadvantage here is that it's not very generalizable and it takes up a lot of space to have. So you have, like I said, like 500,000 training points, awesome, right? But you have to save all 500,000 training points with all of their features. And so you can imagine that's not going to be the best thing versus other machine learning models, which we'll see. Basically, it summarizes, it kind of incorporates that information into the model. So you can basically, once you train it, you don't have to worry about the rest of the training anymore. You can just hold on to that model and just use that over and over again.
So what if I had a situation where there are two labels, which could kind of be a logistic regression problem or a case, like if I have a situation with two labels, how do I tell if it's a logistic regression problem or a K-Nearest Neighbors problem?
So you can actually do either one.
Okay.
And so it's more like you should classify this as a classification problem. So like there's classification problems, which are supervised learning, right? And basically figuring out which algorithm will perform well. And sometimes it just comes down to the fact that like, let me just go ahead and try out multiple algorithms and see what performs well better for this data set. Sometimes as you get more practice and you're kind of more familiar with the data set, you might get a feel for understanding like, oh, this tends not to perform very well because, like I said, like with the generalizable parts. Logistic regression, I like to say it's kind of like the baby step to like classification. It's kind of like, it's relatively simple to like implement. You can do logistic regression for multiple classes, not just binary, because you can basically say, oh, let me just test one, class 0 versus all the other classes, class 1 versus all the other classes, class 2, all the other classes. So you can actually do multiple classification, like multiple label classification. But yeah, I would say K-Nearest Neighbors, the reason why is that it tends to not perform very well, it's not very generalizable, like I mentioned, and it takes up a lot of space. And this is something I don't think the curriculum mentions, but it's kind of an interesting concept. There's a theorem, I can't remember, conjecture, I should say. There's conjecture, I'm gonna have to look this up again, but basically says is that machine learning models basically all perform the same over a given amount of time if given the right amount of data. And so it turns out it's not necessarily about the models themselves, it's about really saying what's the most efficient use of your time to get to something. And if there's more, like if you can afford to keep all of this information on a server where you don't have to worry about it, you're like, cool, K-Nearest Neighbors, like it's simple, straightforward, I know how it works, go with it, kind of like a first step kind of deal. But as you kind of go into like, okay, how do we deploy this out, to something like, what's the use case of this? Like, how are people going to use this, model to make predictions? That's when you have to start considering, okay, like what are the disadvantages for not just how we train it, but also like what we do afterwards done. Kind of a real world example of this. I know like Google's developer conference, they had talked about taking their on device, voice detection. So like, when you say like, hey, like, tell me where the nearest restaurant is, right? It normally would have to take that information, send it up to the cloud, process it, and then send it back down. And that's because their model was about like 100 gigabytes. And so there's no way you're going to fit that on a phone. Like it's just not going to happen. And they were able to get it down recently, down to something like less than a gigabyte. So like, which is still decent size, but it's like, that's pretty significant. And so like when they're able to get that model down to a gigabyte, to be honest, I don't know what kind of model it is. But the point is like they can get it now on a phone. It's a different kind of use case. Now they don't have to send it up to the cloud. It's more instant. It's also, privacy reasons and stuff like that. You can imagine all these different reasons why you'd want that. And I think that's a good thing to think about as like when we look at these models. of like, not just how they perform, but just like, how would they be used in the real world?
Thanks.
Okay, does that answer stuff? Cool. All right, awesome. Well, cool. Yeah, so that's kind of K-Nearest Neighbors. Next time we'll talk about section 34, which I believe is decision trees. So we'll talk about decision trees and we'll see how those work.